We'll speak about performance analysis and troubleshooting methodologies for databases. Raise your hands who are working with databases and troubleshooting methodologies. Do you work in MySQL, Postgres, other databases? Do you know other databases apart from Postgres? Oracle? Who's doing that? Oracle? Other databases? Okay, great, you know databases. We'll be speaking about open databases more than Oracle, but most of it will be applicable for Oracle. Why is that? I'm keen on working on just performance databases, because in many apps, databases are sitting there whereby there are performance problems. Oftentimes in my own practice, I come along to our customers, they say, our app is stuck. Okay, it's stuck. Why do you think that it's about databases? Because it's always about databases, the customers answer. Oftentimes, in point of fact, they are right, by the way. Why databases create such problems for us? Why do we need this troubleshooting to be done? I think that databases, even if it's a distributed database, typically it doesn't scale up in a linear way. Unlike web applications, whereby for customers we can make 100, 500, 1,000 web servers and scale up that way. As to databases, we cannot quite succeed with that. Databases are very sophisticated things. A lot is happening inside them, and oftentimes they're not altogether good the way developers are perceived by them. We send queries, transactions, questioning them what's good, what's bad to those transactions, and it's quite muddled up. Why do we have to do with databases from the standpoint of working with performance? There are several things here. For example, troubleshooting, of course. When something is stuck or frozen, we have to figure it out, do the troubleshooting. Why it is that to resolve the problem? Second task in performance, actually, if we are working at performance of database, when we work, it could be capacity planning. We should plan the resources, but one way or the other, when we have to figure out how much do we need in resources, like hardware, what type of hardware we need, how do we plan capacity so that our system will be run smoothly. Next issue, which evolves, even when the system is operating, oftentimes it's non-efficient. We'll look at our bill and hosting provider or clouds or whatever, we think, oh shit, that's a lot, that's an awful lot. We would like to pay much less to optimize it. It's about cost and efficiency optimization. People on the other side would like us to pay more, but we're on the other side, so we would like to pay less. And also, we should manage changes. There could be different changes on both sides. On one side, what we launch when we launch a new version of a product with new functionalities, new queries, it behaves differently. And on the other side, the change of infrastructure, new versions of databases, OS, whatever, some other components which are changed, they all can impact performance, and of course in the software, and engineers and developers are saying that new is always good, but it's not always when something new is something good. Sometimes we have to do troubleshooting. While mindful of the system, we should look from two different points at it, two different points of view. From the standpoint of the developer, app developer, database is a black box. We send queries, it responds. We think that it can answer any response, even if it's quite shitty. And second one is it's DBA or guys dealing with those databases, it's white box, it's DBA and ops. When we look inside what is going on and why, we try to figure it out, and we debug everything. If we are talking about databases from the standpoint of black box, how can we identify and figure out that databases are working in the right way for us? Of course, it's common knowledge that database is to be available. Unless we can connect to it and do the query, everything will be bad. Our query should be responsible for acceptable time, response time. We would like it to respond for us in the correct way. Correctness is important. It's common knowledge that at the end of the day, you can actually optimize any database, drop all the tables, labels, change something, but the result should be right as well. And then, of course, and we mentioned that for us, by the same token, if we are looking into the black box system, we know how much it costs. So performance or the cost of performing these queries is important for us. If we look inside the black box, oftentimes, apart from these high-level parameters, we could work with the lower-level parameters like hours it's load, how we load the system, how many queries are performed, what they do, the use of capacity, processors, or disk and network, so on, and of course, while we are at it, we can look at different lower-level problems with hardware, with OS, with our environment, and at this level, we can resolve the problems of scaling, capacity planning, and so on. Mindful of the troubleshooting and database analysis issues, which approaches do we exercise? In point of fact, most of the companies, actually, if you come along and ask them, okay, you encountered a problem of performance of database, how do you troubleshoot? Approaches are very much similar. The guys are saying we enter Google or Yandex for that matter, depends on who likes what, and we are hopeful that we'll find something which suits us, which could be the problems which evolve along the way. First of all, the results. There could be a result or there could be no result at all. What's interesting is that if the problems are very simple and straightforward, typically you'll find the answer. If the problems are less conventional, we look through Google and we'll find a not awful lot of different prompts and tips we may try to apply, but they're too far-fetched from us. Another thing is that it's very difficult to train people. Tell them, go and Google things. I don't think it's a good approach. The most important thing is it's very hard to automate all that, especially for big systems. The idea is that we would like most of the problems which evolve along the way, those problems could be resolved automatically somehow. But if your idea is that you should Google it, then to automate the decision which is out there at Google, it's not possible in most of cases. So towards this end, some methodologies are around for us to deal with that. And we'll also talk about 3 of those methodologies. Most popular, its use by Brandon Gregg, utilization, saturation, errors method. By RAD, it's rate, errors, rate, duration method, Tom Wiki, and golden signals. Let's start from use method. Use method was developed by Brandon Gregg. First of all, to analyze the performance of the systems of different servers. What is he saying about it? Use method is very enabling. It helps us to, or not very enabling, it helps us to resolve about 80% of problems with maybe 5% of efforts, because there are different alternatives here. What should be we aware of? This method does not guarantee that having passed through its checklist you'll deal with all the problems. Maybe you'll have to dig deeper, but for most of the problems the decision will be found in a straightforward way. What's good for use method, the beauty of it that there have been developed checklists for most popular OS, first of all for Linux, via which it's possible to get through and to check out what is around, what is in existence. Use method could be worded in one very straightforward sentence. For every resource in the system, we would check the utilization, saturation, поглощение, насыщение. Well, saturation, I've been thinking about the Russian version the speaker is saying, and also errors. So, as to those terms, use method identifies those terms. First of all, it's resource. We mean all the physical components, physical server, functional components like CPUs, disks, and internal buses, network interfaces, so on and so forth. What is a utilization all about here? It's the average time when the resource was busy servicing the work for us. What is a saturation? Saturation is the degree to which this resource had been overloaded, when it had extra work to do which it couldn't service. Oftentimes there is the queue of queries, but that component was busy, so that extra work was not serviced. And errors is the count of the errors altogether. As we have mentioned, the major resources of use method, major capacity of it are several classes of that, but of course it's common knowledge that we can talk about much deeper parameters. Mindful of CPUs, we can look first of all at the CPU cores, sockets, or hardware threads, virtual CPUs, because some of the parameters of utilization could be interconnected by the processor, by the CPU. Mindful of memory, typically we'll look at the size of the memory capacity, and it's easy to be measured in modern systems. We should figure out to which extent the bus is loaded. Network interfaces, from the standpoint of those network interfaces, there are two parameters for us to look at. On the one hand, we are interested in the parameters, input-output parameters. On the other side, the disk size is there is no more place in the disk, or when we are approaching the situation when there is very little space left on many modern devices, the performance is dropping. And secondly, it's common knowledge, if we run out of the space on the disk, database will stop being operable. And controllers, same goes for controllers, storage controllers, network interfaces, and so on. How do we use this use method with software. First of all, we should be aware that any software whatsoever from the standpoint of functionality and performance is based on hardware. If there are some troubles at the lower level from the standpoint of software operation, and they will be shown. But in software, there are some extra additional software resources which we should also look at. For example, the mutex logs, redrive logs, and so on, synchronization, concurrence objects. Oftentimes, when those objects, those logs are proactively used when they are hot, it could limit performance, even when physical technical resources are yet available. File descriptors, by the same token, oftentimes apps start working in the wrong way, or there is a failure when we run short of available file descriptors. Same goes for connections. It could be directly as file descriptors or some other interfaces as well. Anticipated local ports and some other resources of the kernel to create those connections and so on. As I have already mentioned, the beauty of use method is that it has got a rather good and proven track record in Brandenburg. Lots of people use that method. There is a lot of literature, references, and publications available. It could be used broadly for different systems. We have got a detailed checklist. Which drawbacks use method has? First of all, it requires very good and thorough understanding of system architecture. Just by one example, if I'm looking at the system in the cloud, I have to say, okay, this database is stuck because the disk could be stuck, but it's a network drive, and it can get stuck because the network can get stuck, and the network gets stuck because maybe it's overloaded. So it's very difficult to figure out it rapidly. And secondly, in the example I mean about the cloud, maybe there will be even no default usability. We may not know what is going on outside the limit of this view. And also we might require an access which we might not have, an access to low-level resources, and how should we monitor those resources, and if our environment actually is not ideal. But access to database, there's database the service like Amazon RDS, Aurora, Yandex launched as database service as well. But one way or the other, the access to details is very much limited. And also, as to cloud computing, there are lots of limits here as well. There are some extra problems which evolve. It's common knowledge that there are different customers, lots of them, who use one and the same infrastructure, notwithstanding the fact that everybody is trying to isolate those clients from each other, to detach them, customers from each other. Some succeed and some don't. We don't have full isolation between the customers. So on top of the fact that we should be aware as what is going on in our system, what the load is, we should figure out that certain things might happen due to when something evolves in cloud infrastructure.
That influences the process, and it's clear that the same information about the hardware, virtualized also, it could be not always full, complete and true. And next interesting item I wanted to mention is queuing. You know what it is? Yes, correct. And why I speak about queuing and show this image? When we speak about queuing, In the concept of saturation, concept is quite simple. We say there's a certain resource, and either this resource is doing the work or waiting for a possibility to do the work. In reality, in modern systems, everything is not quite that simple. If we go down to a lower level, the more we can understand about those specifics, like you see as in fractal picture, the more and more details, and you understand more. And the developer who writes the application working with a database, he just sends a request, and the database sends an answer, and it's like it works. And if we go deeper, one level deeper, then the request doesn't do anything. It's just waiting for the database to react. Or processor could be overloaded. It could be Linux processor. It is scheduled already, does some process currently, but the point is probably also waiting for something to do even those processes, and we're waiting for results from memory, for example. And that is important parameter, important to understand what is behind it, because that allows us to optimize our efficiency. If we have a processor loaded to 100%, we can often look up at APC how many instructions they do per clock, and to understand how much of the program is really executed and then waiting, because cache is not used effectively, or some other bottlenecks, TOB, context switches are flashed, and if we optimize those items, maybe we will have an improvement of productivity. I remember the Michael Stonebreaker. They did analysis over the databases, modern day databases, and that analysis showed that 90% approximately of resources, time-wise, were spent to overhead, like slotting, mutex, and overheads related to operational system function, and only 10% of time were actually doing useful work on the database. It's unusual. Research is also quite common that not whole resource is used for something, but just part of it. Concept is interesting. You don't remember all that. You don't need to try to remember all that. This is an example of checklist for Linux. As I said, there are checklists for various operating systems. You should visit Brandon Greg's site to find those there. In Percona, we develop a product for monitoring. Despite the fact that it's not yet finished and not yet suggest to use a single method, we try to make our product more flexible so that it supports various methods, as well well-known methods, as well as some other methods. We speak about CPU utilization. In particular, it is clear that this is a practical case. There is one thing to mention here. I remember that many graphs shows I/O wait as part of the utilization of the process. I/O wait is not utilization of process. It is idle state for processor. When processor is waiting for input-output, if the disk would not be going slow, then processor could be working better during that particular time period. What we also added is a change in the CPU saturation. I don't like the Russian term for that. I would continue using the term saturation rather than the Russian equivalent, and that allows us to understand the average run queue for processor that we try to normalize for the number of cores. That, in general speaking, allows us to understand while the processor is 100% loaded and we have 4 processors, for example, 4 cores, and they're all running, utilization 100% and no queues, or it could be 100 cores, not 4 cores, then on average we'll have 25 processes per physical CPU core. Then saturation will be quite high. And second thing which we try to look here at is maximum utilization of processor core. Because if we look at standard values, that normally is average per for all cores, but some tasks are not scaled up to be processed at many cores, and they do that on single core, and we want to understand what is the load on that core. If there's hot core overloaded, then we should think about the solution. So despite the utilization of being high, we need to look at in more detail what is actually behind that. And the second variant is the processes. We can try to understand more about the processes, and we can present them in various views, and that would allow us to understand the saturation or load, both process point of view as well as processor, CPU, and this is the number of processes running, and here we have some sort of quite a number of processes picking up into a much higher intensity. Physical memory, from that point of view, everything is more or less simple. We can look easily up how much we have in total memory, how much is used currently, how much is available for cache and buffering. What else happens quite often that we look at is virtual memory. What is virtual memory? It's physical memory plus swap, right? On the one hand, if you have database and do you swap that working actively, but if the swap is over, then the database either will get an error in memory allocation, or in modern systems it will be just killed down by that OEM killer, very angry element, and that will start crash recovery in the system. That should be prevented actually, and that's why we should look at virtual memory, whether it's not yet completely exhausted. Next item is swap activity. Many people, when I hear them, they say that even if we have swap, we don't want to use it all the time or regularly. This is not quite correct, because currently in the system there are libraries, there are some blocks of memory that are used, but this is a good solution, good configuration for Linux to simply remove swap. But what we don't want to have is that there is constant swap, big swap input output. If it is one time operation, after that something is stored there, well, that's more or less okay. But if it is every second that this is used, then this is not good for productivity, overall productivity, and we have to do some something about that. If you work with a database, that means you send too much data to cache, and that means probably need to be reduced, or some other SNOOM problems, and some other problems could be resulting from that. Now, from the point of view of disk load, standard is that we measure productivity of disks from the point of view of I/O operations or bandwidth, kilobytes, megabytes on disk we measure. And what is interesting is that modern storage, if we look at cloud, at your physical SSD storage, that all is quite tender, can behave differently depending on the phases of the moon, you know. Many can say that I am hot now, I will switch on throttling, and or I would like to do today garbage collection. And that is why to rely on some bandwidth or some operations of input-output that you can do, not always is available. That's why we have to look at the disk load or load average that will show us what is the outstanding disk I/O requests. And here you can see that in this block, for example, the queue is more than 50 I/O requests has risen to that level, and that means very likely that the disk is overloaded. The modern storage SSD, if disks were quite simple to measure, because every rotation could do one operation, actually, input-output per cycle. SSD, depending on the vendor, it could be inside quite a number of parallel devices and operations, 64 parallel requests can be processed, and optimal productivity is achieved with that type of memory absolutely differently, and their response, latency, with the increasing number of parallel clients is different compared to disk. Next, a different thing is when we look at disk I/O latency. That is very unstable, as you see here. Also, we try to compare that with average. With average latency for read and write. And if we have, like here, that all samples are above, all of a sudden standard time, typical time, that is not always the case, and it is related to productivity. From the network utilization point of view, we look at how many kilobytes, megabytes we send, receive. Unfortunately, I didn't find in Linux kernel how we can retrieve information about what is the queue size in these networking devices. If you know, any of you, where I can get that, please tell me this. It'll be interesting to look at the queue size, but so far I didn't find that. From the network point of view, it's very important to consider errors, because unlike disks, where you shouldn't have any errors at all, modern disks, and the network, unlike a disk, network allows mistakes or errors that happens more or less regularly, and it is important that they are not too multiple. From that point of view, we look at local errors, that your local device, how many packages were not sent and dropped actually, or whether there were some other glitches or checksums, and in the same way we could do that for the global network. When you work between two endpoints, where in between there could be quite a number of other disks, then it makes sense to look at the retransmit segment number, because retransmit is not good. That means resending, and that increases the latency compared to standard. If the database normally works only with local devices, and latency is smaller, but it transmits the TCP/IP level would cause quite a problem there. From the database point of view, we look in particular now at MySQL, number of requests, database processes is important factor for us. Here, for example, something strange was happening when we had a number of requests that database could process was dropped all of a sudden, and here again, in order to find out the reason, you have to look at some other graphs and some other statistics, because maybe there were a number of very sophisticated or complex requests, and the database got overloaded just because of complexity and not the number of requests. And there could be different requests that reads one line, for example, in primary code, or that could be requests that you have to process millions of those. I love to look at the lower level in MySQL. In DB, for example, search engine, you have a possibility to look at the number of lines, for example, that was processed in a second, because lines, of course, could be also different. It could be lines that are quite substantial. It could be a couple of lines. If we look at MySQL situation, then the simplest way to look at it is from the point of view of how many flows or streams we have in processing, being processed. Many of them are busy currently. Here we have standard level, number of requests were processed. Here we all of a sudden have this increase to a certain new plateau. The number was higher, and that means the load was higher too. And quite often it's the case that 10 times, even more times higher, the number of requests all of a sudden increases that number, and then we have to do something about that. Now let's go over to the next method, which is red method. Second, red method was developed to work with microservices. And we speak about microservices. In reality, we want to analyze productivity of the whole infrastructure. And that means that we consider all our elements of the structure as cattle, not pets. Metaphor, if you don't know that, that means that if we have home animals like a doggy or a cat or maybe a guinea pig, then it's clear that stress of each of those pets is quite high level event for us. But if we look at the cattle in agriculture, then you don't that much get concerned about each particular cow every day, because you have so many, and sometimes you even help them to die in order to just remove that irritant. That is the approach. Quite often the case of microservices, that we look at their impact on physical resources. It could be clustered, responding to requests. Some of the element of that cluster, Kubernetes decided to drop and then later left, and some other node. Then in there we have different effects. But
Using a red method, in one phrase, it's the following. Actually, for every resource, for every service check request, we should check these things so that they should be in line with SLO, service law objective, that is, that they correspond to the criteria which we would like to have for the performance of this type of query, for this endpoint. If we have got some microservice, there could be different requests. Let's say we're going to show one type of goods that should follow within 10 milliseconds. If there are lots of different items and very sophisticated and complex requests, it could be 1 second, depending on requests. There could be different requirements as to the admissible time and what should we expect, what would be the number of those requests. If we are looking at red method at the database level, of course, it's crystal clear that we can look at the service level directly, or likewise, we could apply it oftentimes to databases, database servers, and we should look at the resources, different components of request, because each component or type of request, like to retrieve this and this type of data from database and so on, it could be perceived as the type of request. So what's the beauty of this method? What are the benefits of it? First of all, what are developers thinking about? They want their request to be responded correctly and rapidly. Actually, that's what red method is all about. It doesn't require very deep understanding of the infrastructure and very detailed access to system resources. It doesn't require all that. But drawbacks are there as well. It's not as well developed as use method, and for red method, actually, there are no well-developed checklists yet. And I would also say that oftentimes it enables us to figure out that, let's say, the problem is this one. We have a database, and for some reason it gets stuck when it performs this request, but it says nothing as why it happens. It gets stuck because there are some joysticks or other requests which overloaded the system or plan, suddenly change whatever. This method doesn't specify that. As I've told you, we can apply this method to different types of queries. And here into SPAM, we've got such a function that we show queries which generate most of the load upon the database. And for each query, we can check out the rate of those queries, how much was generated. By the same token, we could look at latency. And the response rate, and we can also check out the distribution of the latency, minimum and maximum, 95 percentile, whatever. Why is it so important? Because oftentimes when we check out queries in the database, it's not the problem with average queries, but let's first the queries stuck for big clients, so on and so forth. Unless we sort this out, more and more people will get stuck, creating problems for the other people as well. Another interesting implication related to that, what we could also see is that in Percona server we have good statistics for what we call response time histogram when we make the breakdown in time for the response time, and oftentimes we can use criteria which are important for your app. You can see how many queries were there which are outlaying the time which is admissible. In this graph, you can see the number of queries which are jumping, and some are very slow, more than 10 milliseconds. We can check them out of very slow, more than 100 milliseconds. Oftentimes, it enables us to troubleshoot before actually later on those problems will be obvious. Then 4 golden signals. They are part of the book, which is called which was written by guys from Google, SRE book. Was it translated into Russian? I'm not sure. It's monitoring distributed systems from SRE book. It's a great book. Lots of very good things described in it. And there is one part about monitoring of distributed systems. They are referring to those 4 golden signals which can be used for alerting, and by the same token for the troubleshooting, trend analysis, and so on. What are those 4 golden signals? First one is latency. It's the response time, traffic, or the number of queries and bugs. So it's also errors and saturation. So latency, traffic, errors, saturation, 4 golden signals, but they don't identify it at such a low level as in this case. As to just latency time, latency or response time here, we would like to look not only at the average response time, we would like to change the distribution. That's very important. Secondly, it's extremely important for us, mindful of this response time latency, we should look separately at successful queries and bugs. Oftentimes when the system is damaged, the following thing happens. Some part of the queries get stuck, latency increases drastically, but some queries are developed with a bug, and those queries in the bug are very rapid, like databases. It's overloaded with application. It's short of available connections. When a new query comes along, we try to connect it to databases, and I cannot do it. The bug happens, but it happens very rapidly. But those 5% of queries which were able to get connected because those latent queries were developed, actually the latency could be 5 minutes response rate. But unless you divide them into bugs and no bugs, the average response time could be within the norm. Like a joke about the hospital, they think that the average fever temperature is 36.6 because 10% of patients are dead, no temperature at all, and others are running fever temperatures 40 degrees running fever, but on the average everything's all right with our patients. Some are dead, some are alive in the hospital. That's very Russian joke. As to the traffic, which is identified here more broadly, oftentimes it's the number of those queries, but in some cases the systems could work not in such a mode as the query mode, but it could be the number of users, the number of concurrent jobs which are active now. Errors, from the standpoint of errors, there are 2 things here. Just error codes, it's very simple. We send a query and they respond, it's a bug. But some bugs which are more sophisticated, it's much worse if we receive the wrong content. In serious systems, typically there are some checks which check up not just bugs, but also whether the content is correct, and also from the standpoint of saturation. I think it would be relevant to figure out to which extent our capacity actually how full it is. Did you use it to the utmost, this capacity? If the traffic is good, actually it's good to have forecast whenever possible and to do the measurements and to have the capacity planning work to see how what amount of resources are yet available. From the standpoint of databases, how can we apply all this? As I have mentioned, you may look at the queries for different endpoints. You could look at different queries and different latency or response rate distribution errors and this type of query. Traffic-wise, we could look at the number of queries of the same type. It's important if it's a specific kind because oftentimes those things are rather stable and characterized in the best way the load upon the system than just a number of queries. Mindful of errors, we could look at the errors on the code. It's error codes, simple as that, and also we should look at wrong query responses, which is rather challenging. That's quite hard. And as to the loading, we look at the amount of resources used and usage, but also we look at the connections, whether there are connections available, look at the disk space, and so on. And what are the benefits of this golden signals approach? What are our perks? This approach ensues from Google. It's common knowledge that they do have a vast experience of managing big systems, big networks, and they have got a good book, and there is a good book available on that topic. And it's common knowledge that it's more drawbacks for frameworks for monitoring than for troubleshooting as well. And there are no explicit checklists for it yet. So takeaways. What's great and cool is that over the recent 5-year span of time, methods of analysis of performance were broadly disseminated. Recently, awareness raising was done versus what was 5 years back from now for databases. Instead of this, Carrie Malcolm, that guy, and used for Oracle, he popularized our method, but didn't see many other methods. What else is interesting, notwithstanding the fact that we looked at 3 different methods, there are lots of different guys actually, and we see that they are looking at almost the same things, simply from different angles. And last thing for me to mention here and also to ask from you, do you know what Percona is? Percona, well, great. You may know that we are engaged in MySQL. Somebody knows maybe that it's MongoDB as well. That's what we're doing. But now also Postgres. We're engaged in Postgres as well. From the standpoint of our practice, supporting consulting, so Percona is supporting PostgreSQL, and we'll be developing different tools for Postgres as well. So that about wraps it up. I'll take your questions, Ivana. Thank you very much.
The first person whom I have already seen.
Thank you. Спасибо, Петр, за ваш доклад. У меня вопрос такой.
Thank you, Piotr. I have a question. You've shown us very colorful graph. On the website of Percona, there are some ads and dashboards. Do you deploy it someplace else? A lot of very useful information, but we need more information. Well, as to all those graphs and fancy pictures are there from SPM, while when Prometheus and Grafana are used, we have been working with them, we developed that, and there will be also more of those in future as well, of course. And if you are just using them, let's say Grafanos, Prometheus, of course, it's common knowledge that you just download them from SPMM or from our repository and customize it and use it for your own ends. And also there is another interesting implication here. In open source, if you need more graphs, you can write them and to submit the pull request. Well, thank you, I've got it. Simple as that. Well, if there are links to your repository, you can just find them. There is something else. I saw in different big companies, I saw another approach towards monitoring of big systems and performance analysis. When we identify at least 5% of queries and do full profiling for these 5% of queries, after which it's not just about utilization of the CPU, but how many rates we spend for performance of one query, how many disk blocks we obtain for this specific query, and all those gimmicks enable us to have much more fascinating benchmarks, like when everything was cool and then all of a sudden the average number of reading disks per query increased. Maybe you also have a name for this or some method. What you're talking about, I would say it's tracking. You're saying that we dedicate, let's say, 5% of queries, do tracing for them. We also store this information. This is a good approach with such kind of tracing. There is open tracing as a framework, as a tool. There are lots of tool chains for that, and actually for tracing, yes, we contemplated that, but we didn't study it deeply. Oftentimes it's done at the level of APM, application performance management, when many cloud solutions have App Dynamics and others, whereby they instrument applications, some queries and apps, and further on there could be a detailed tool chain on all the services they do. So we should be aware that for this query in application, such database queries are in conformity and they were working rapidly, or they got stuck due to this and that reason. Well, in work on query analytics, if you have got this Percona server, and is there the information, how much information it's retrieved and how many disk operations, so it's all in query part of query processing. Problem is that apps typically doesn't have many SQLs, but different types of queries. Yes, application, yes, an application. That is why I reiterate is done with application performance management. When there are different transactions of levels of application, they could be profiled differently. My idea is not about tracing per se, but about the fact that we can see some kind of a state of our system. And in ideal world, we could trace the entire. We should trace entire system, and we'll see that for all the queries for 200 millisecond, now it's 600 millisecond, and some benchmarks increased as well, some specific ones. That would be a good idea to do such kind of tracing. Thank you very much for your presentation. I have a question about use method and CPUs. Of course, it's we normalize it, but there are arguments that when weight is increasing, these technical resources the same, but we are starting to look at in a low temperature of several CPUs. In your experience, should we normalize it? Why do you mean? What do you mean by normalizing? We may calculate multi CPUs summing up, and it doesn't matter how many CPUs are there. I didn't show you some graphs what we're doing in our system. We do the breakdown into this saturation into CPU part and IO part. That part which is related to CPUs, we normalize it on the core because it's relevant from the standpoint of IO load data. We do not normalize it because, in point of fact, typically it's very little we know about this or that device. There could be the same block device, and if it's the disk, it's one thing.
One request. If more, then there's a queue. If SSD device, Sun, for example, it can do in parallel 100 maybe more, then it makes sense to look at that at the same time. That's why I do not like Linux load average parameter, because it tells us, very abstract value. What is average? 20? Good question for an interview. Load average 20. What is good or is not good? Any question, any answer will be incorrect. Load average. From the point of view of what we look at, we need to distinguish which resource is actually measured, because really any overloaded resources is a problem. Any other questions? Thank you very much. It's not a question, probably a comment. Many methods, troubleshooting, performance analysis, you mentioned one method only briefly, but it's important, I believe. Developers should be trained so that there's no black box and better understanding. A lot of problems with productivity is developers, because developer cannot do SQL requests correctly or queries correctly without knowing architecture of the DB, of the database. Developers should know that. So 70% of performance troubleshooting is developers. 30 is post-factum analysis of what the suggestion came to. That's correct, yes. In addition, I could say that our tools for analysis of queries is used by developers. We recommend it to them. We say, people, install it on your testing system and explain to your developers how to make use of those tools. If it's here like this, then it is wrong, so that they would figure out. If they don't understand all details, then at least they know that there is this type of assistance available, and if your development team allows to issue bad queries into production, then you have to do something with the development process that you have. It is quite possible that you will have to chop heads of half of your developers and maybe remunerate the other half or something else.
Так, ну что, благодарим докладчика еще раз.
Already we get deep into details. Okay, thank you again.